Aniruddhan, and this is my video demonstration for the project Automating RF Circuit Synthesis, specifically for the noise cancelling LNA. The given specifications are at 1 GHz and they are as follows. The differential gain needs to be greater than 15 dB, the noise figure needs to be less than 5 dB, S11 needs to be below minus 10 dB, IIP3 needs to be greater than minus 10 dBm, and the power dissipation needs to be minimized. The first step is to build the schematic in Cadence. I have done that. This is the common gate stage and this is the common source stage. Both of these have been biased using AC coupling capacitors and current mirror biasing, as you can see. And the DC operating point has been chosen such that the input impedance looking in from this input port is around 50 ohm. It's not exactly 50 ohm. The code will take care such that the S11 spec is met. Now I'll run you through the code. So the grossly important details of the code are as follows. This is the definition of the loss function. The specifications have been written and the rectified linear unit loss function has been chosen. The loss is just the sum of the gain loss, the S11 loss, IDD loss, noise figure and IIP3 loss. And the gradient has been defined for this particular case. Depending on the case, this can be edited such that for each specific circuit, the gradient function can be defined. Moving forward, this is the update equation. This also keeps on changing depending on the circuit. I have tried to make the code as generic as possible. This function evaluates the DC operating point. This function reads the S parameters. This function reads the noise figure. And these two functions calculate the IIP3. Along with this, this function basically calculates the AC gain. This function is responsible for optimization. This function performs the sensitivity check. This function gets the process currently being done. This function performs the temperature sensitivity check. The earlier sensitivity was just a parameter variation sensitivity. And this function prints the loss function at various different temperatures from minus 27 degrees centigrade to 100 degrees centigrade. This function prints out the loss function during different processes. This function basically analyzes the voltage variations and prints the loss function. This is the main function that takes into account all the above described functions and integrates the same. These parameters have been chosen from the operating point specification as I described earlier. The same thing goes here. There have been two netlists. This netlist basically is used in calculating the DC operating point, the AC analysis and the S parameter analysis. And this netlist is exclusively used for HB analysis. So that is why there have been two netlists. Now I will run the code. As you can see, the code is running and several files have been created. So as you can see, the first operating point has been printed. The parameters have also been clearly printed on the screen. this is the just the initial operating point. Now the algorithm has started working. As you can see, the AC gain has improved, noise figure has also improved, S11 is also better, and IIP3 is also improving. Again, the loss has dropped significantly. Just for the sake of this video, I have considered only 10 iterations. The code can be run for several larger number of iterations, per se 100, and the best netlist can be chosen depending on constraints based on power dissipation, sensitivity, and process variations. The code also picks out the three best netlists. By best, I mean the netlists that have the least loss function and runs PVT variations and sensitivity check on them. And depending on which netlist performs the best, we can pick that netlist. All of those netlists would be saved. As you can see, the loss function is just keeping on going down. The noise figure is improving. IIP3 is also improving. As you can see, some specific netlists have been saved recently. These are the netlists that are in the top 3 based on the loss function. So as you can see, the loss function as a function of iteration number, it keeps on going down. And as described in the earlier video, the loss function is a linear function of several different individual loss functions, the S11 loss, the ITD loss, and so on. And as you can see, the loss function neatly goes down. I'll continue running the code. So now PVT variations and sensitivity analysis will be performed on the 3 best netlists, and depending on whichever netlist performs the best in this, we can pick that netlist and use it in our design. So now the temperature analysis is being performed. Temperature analysis is done at 4 different temperatures: minus 40 degrees centigrade, 0 degrees centigrade, 27 degrees centigrade, and 100 degrees centigrade. And since I told 3 best netlists, the 3 best netlists have a loss function, a loss value of 1.653, 1.597, and 1.544. And as you can see, the third best performing netlist, or the first one that was saved, has a loss function of 1.6533 at 27 degrees centigrade, which is the same here. So this confirms that the code is working fine. The temperature analysis is completed now. Now the process variation will be displayed. As again a matter of sanity check, the loss in top TT process is exactly the same as it should be at 27 degrees centigrade, and it is. So that confirms that the code is written correctly. And again, depending on the process or the operating temperature or the supply rails, the process temperature and supply voltage rails can be modified accordingly in the netlist, and the code will take care to optimize again. Now the process variation analysis is complete. We'll move on to the voltage supply variations. From the temperature analysis, it appears that the loss function is increasing with temperature. So the temperature sensitivity should be positive. That we can confirm with the temperature sensitivity, which will be displayed slightly later from this point. And again, the loss at 0.9 volt is 1.653 as it was at 27 degrees centigrade. Again, another sanity check. And as expected, the loss goes down with increase in supply voltage. Now the sensitivity and temperature sensitivity checks are being done. As expected, temperature sensitivity is positive and the sensitivity is coming out to be negative in this case because only for 10 iterations, just for the sake of this video, we have not yet completely hit the local minimum. Since this will take a very long time to record, I have just restrained this for 10 iterations. However, in the report, I have run it for more than 100 iterations and the results have been presented. Now the same PVT variations and sensitivity analysis will be performed for netlist 1 and netlist 2. The numbering goes like 0, 1, 2. So whichever netlist based on our sensitivity spec and PVT variations, we can pick the best performing netlist. The second best performing netlist had a loss of 1.597 as you can see here, and the same comes out here at 27 degrees centigrade, which is again a sanity check that the code is working fine. So the temperature analysis for netlist 1, which is technically netlist 2, is complete now. and again that loss in top TT process is still the same as at 27 degrees centigrade, which is a very clear sanity check that our code works fine. The code takes a significant time to run because the model file is slightly complex. For relatively simpler model files, the code runs much faster. So now the process variations is complete for the second netlist. We move on to the supply voltage variations. Now the voltage supply variations check has been performed. Now we move on to the sensitivity. This is the last for this netlist. As expected again from the temperature analysis, this temperature sensitivity is positive, which implies that the temperature analysis prediction of loss increasing with temperature is correct. Again, another sanity check that the code is working fine. And as described earlier, the sensitivity is negative because we have not truly converged to the local minimum in this case because the number of iterations are less, merely for the sake of recording this video. This is the final netlist on which the PVT variations and the sensitivity check will be performed. Now, currently we are at the temperature analysis phase. Now the temperature analysis is complete. We move on to the process variations. As you can see, the temperature sensitivity has been going slightly down from netlist 0 to netlist 1. We will see what happens in netlist 2. Now the process variations are complete. We move on to the power supply variations. And as you can see from the temperature analysis, the loss is increasing with increase in temperature, which means the temperature sensitivity needs to be positive, which can be confirmed later. And again, as a matter of sanity check, the loss at 27 degrees centigrade, top TT and 0.9 volt needs to be the same, because that is the default specification of the netlist which we have considered. And as expected, the loss decreases with increase in supply voltage. And as expected, the temperature sensitivity is positive and it is lower than the above two, and our code has completely executed and it has executed successfully. Temperature sensitivity for netlist 1 is 0.03366 and here it's 0.0034. This is clearly the best. So if temperature sensitivity is one very critical parameter for me, I would pick netlist 2 to be the best. It has the lowest loss and the lowest temperature sensitivity, and I can use this as the desired netlist. So with that, I would like to close this video demonstration for noise cancelling LNA. Thank you.